Potential transformer. Potential transformer or voltage transformer is an instrument transformer used to measure the high voltage. The primary high voltage winding has a large number of turns and features a special form factor to reduce electric field stress. One end of the winding is connected to the mains and the other end is grounded. The electric potential is distributed linearly along the winding. There are 35,000 turns in the primary winding and 100 turns in the secondary. I will not draw each individual conductor, but I will draw each individual layer. The task is to calculate electric field stress distribution. Transformer operates at AC voltage, but I am interested only in the peak values of the electric field stress, so I'm going to simulate an electrostatic problem with the peak voltage value specified. The winding features rotational symmetry, so I'm going to build a two-dimensional axisymmetric model. Okay, let's start QuickField now. In QuickField, I create new problem. Turns. Next. Problem type is electrostatic. The winding features rotational symmetry, so the model class is two-dimensional axisymmetric. Length you need some millimeters. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here using QuickField tools, or you can import the geometry model from the AutoCAD .xf file. I already have the drawing prepared in the CAD system, so I'm going to import the model. Here it is. Here you can recognize the core, insulation, winding. In axisymmetric problems, the axis of rotation is a horizontal one, and we should only have the objects located above the axis. So switch to insert mode, draw the horizontal axis, switch to select objects mode, select and remove all objects located below the axis. Now let's assign labels. Through labels we can distinguish objects and provide material properties. Switch to select objects mode, click the object to select and assign label. This is oil. Our transformer is immersed in the oil. This is paper insulation. To select multiple objects at the same time, hold the control button pressed. Let's zoom in. This is the paper insulation tool. And this is the cardboard cylinder. And these are the cardboard cylinders too. This one and this one are cardboard cylinders. This is the secondary winding and this is the primary winding. In the secondary winding we have 100 turns. This is the conductor and this is the insulation of the conductor. And in primary winding we have 35,000 turns. This is a simplified geometry model. You see, we do not have individual turns in the primary winding. Instead, we have individual layers. So this is considered to be the conducting layer, and this is the insulation. And this is the insulation. And so on, and I need to assign labels to all insulation layers. So let's do it the fast way. I will select everything and assign label insulation. Well, these are not insulation, these are conductors. There is no electric field inside conductors, so there is no need to assign labels to conductors. I should select all conducting blocks and just remove the label. Okay, now we have paper and layers insulation. The same I should repeat for other parts of the winding. Primary winding has 3 parts. Again, I use the rubber band to select all objects and assign label insulation. And then I should remove labels from the conducting blocks. These are conductors, and these are conductors. Okay, we have assigned labels to the dielectric materials, to the oil, to the paper, to the conductor's insulation, and to the cardboard cylinders. For the conducting blocks, we do not assign labels, we assign labels to the conductor's surfaces. This core is grounded. Hold the Ctrl button pressed to select multiple objects at the same time. For these edges, I assign label core. Now, what about the winding? This top layer of the winding has high voltage electric potential. It is a solid copper foil. I assign label high voltage. High voltage. Then we have the winding layers, and the electric potential is distributed linearly along the winding. Each layer features different electric potential distributions, so I need to assign unique label to each winding layer. This would be layer 1. This would be layer 2. So there are 35 layers in this part of the winding. Now let's assign labels to the second part of the winding. This would be layer 36. $37. And 17. Now I have labeled second part. Let's label the third part. $71. And 98th layer. And the top one is the high voltage. Okay, we have finished labeling the winding layers. Now let's provide physical properties for these labels. Double-click the label name in the tree. Electric permittivity of the cardboard is 2. Electric permittivity of the insulation is 3. Electric permittivity of oil is 2.3. And electric permittivity of the paper is 2.3. Core is grounded, so its electric potential is 0. High voltage electric potential is 35 kilovolts. Okay, now what about the winding layer 1? The left end is grounded. There are 430 turns in this layer. Electric potential is distributed linearly. This is the winding layer. There are 430 turns in this layer. This side is grounded. First turn is grounded, and 430th turn electric potential is 429. This turn has electric potential of 429. Then the winding changed direction. We have the second layer, and the first turn in the second layer has electric potential of 430, and the last turn in the second layer has electric potential of, then another step, and it keeps going up and up. In QuickField you can specify the electric potential as a function of coordinate and get the linear dependency. Now let's check what we have here. Here at this point the x value is minus 90 millimeters. Here the x is minus 90 millimeters. And on the right side the x is this value. So in QuickField I can type in the following equation. The potential rise per one layer is 429 volts. 429. When the x is minus 90 millimeters, we should have 0 volt. X plus 0.09. I should convert millimeters to meters. So when the x is minus 0.09, this will give me 0 volt. And when the x is this value, I should have 429. So divide these by the 0.099618 plus 0.09. When the x is minus 90 millimeters, I will have 0. When the x is this value, I will have 429 volts. You can use our online tool to verify equation. Just type in the equation here, specify the range from minus 0.09 to 0.099618, and press display chart from 0 to 429. That is for the first layer. Now what about the second layer? It is the same 429 volts per the winding length, but it starts at 430 and the rise direction is reverse, from the right to the left. So in QuickField I can type in 429 divided by the minus x plus 0.099618. So at this point at the right we'll have 0, and at the left point we should have 429. So now at the right end we have 0, and at the left end we have 429, but remember we should start not from 0 but from 430. So here I add 430. Let's visualize this equation. Paste it here. Oh, we have an error here. This should be multiply from 430 to 859, as it should be. Okay, I should correct it here. Multiply. In the similar way we specified the equation for the third layer, I can copy the equation I used for the first layer. But remember, the third layer starts not with 0, it starts with 860. So here I should type in plus 860. Let's check this equation, paste it here. 860, 1289. And you just keep going. The fourth layer starts not from zero. There are 3 layers. Each layer raises the potential by 430 volts, so I multiply it here by 3, and so on. Now we have specified the electric potential distribution for the first part of the winding, for the 35 layers. Now we have the second part. I copy this equation and paste it here. But the second part is shorter than the third part. It has only 370 turns, so I should correct this equation. The left coordinate is this value, the right coordinate is this value. This is the electric potential rise provided by the first 35 layers of the winding, and in this shorter layer the potential rise should be 369 volts. The winding dimensions are the following, from this value till this value. Display chart. Okay, and for the 37th layer I'm going to copy this, paste it here. The potential rise, the first part, is this value, plus we have the potential rise by the 36th layer, which is 370 volts. And I should correct the dimensions. Copy this, paste here, copy this, paste here. And the potential rise is 369 per one layer. Now I can keep going, copying and pasting the equations. And this is the last turn in the second part. Now we move to the third part. There are 35 layers in the first part. There are 35 layers in the second part. The third part is shorter, so I should correct these dimensions and the potential rise. The third part has only 250 turns, so this should be 249. And let's check the dimensions of the winding. This first turn coordinate, this value, paste it here and convert to meters. And paste it here. And the last turn coordinate is this value. Paste it here and convert to meters. Now let's see what we have on XY plot. It should be the straight line again. And indeed it is a straight line starting at 28 kilovolts, and the potential rise is 249. Copy this and paste in QuickField. And the next odd layer has electric potential of plus 2 multiplied by 250. This is the equation for the last 98th layer. Let's visualize the electric potential distribution and make sure that the last turn electric potential is 35 kilovolts. Put the equation here This is the potential rise provided by the first 35 layers. This is the potential rise provided by the second 35 layers, and this is the potential rise by the 27 layers, and this is the potential distribution in the last layer. 35 kilovolts, as it should be. Now we have finished with labels editing and can solve the problem. Before I can run the analysis, I should build the finite element mesh. We have a lot of small objects here in the geometry model, so to speed up the mesh building, I'm going to specify manual mesh spacing. Click here and type in the spacing value here, 10 millimeters. And for these parts of the winding, I specify the mesh spacing of 0.25 millimeters. And here 0.25 millimeters. Now let's build the finite element mesh. The mesh is generated. Let's take a look. You can see blue circles here. You can switch them off and on. They are used to visualize the manual mesh spacing value. 0.25 millimeters is the circle radius, and the finite element mesh size here is 0.25 millimeters. Okay, the mesh is built. Now save all problem files and solve the problem. The problem is solved. Let's take a look at the results. And the field distribution doesn't look correct. Probably we should change the precision to be high. Let's solve the problem again. Now the problem is solved with high precision. It took more time. Let's take a look at the results. Now this electric potential distribution looks physically correct. Let's zoom in. I'm going to use the contour tool to select surface and measure electric potential distribution along this surface. You see this contour is built along the first layer. It should be from 0 to 429 volts. Let's take a look at the XY plot. 0 here and 429 volts here. Let's zoom in and continue the contour. Now I will select the second layer. First layer and the second layer. Again, open the XY plot. First layer, then second layer. Add the next segment. First layer, second layer, third layer, and so on till we get the end of the winding where the electric potential is 35 kilovolts. So it looks like potential distribution is correct. Now let's take a look at the electric field strength distribution. Change representation type to electric field strength. Let's zoom in. It looks like the most stressed part is located here between the start and end turns of the adjustment layers. Contour, remove contour, add the contour line here, open the XY plot. The electric field stress value is about 12 kilovolts per millimeter. In fact, you can get the electric field stress value in any point. Just use the local values tool, click any point, or hover over the picture, and you will see the electric field stress value here in the status bar. So this way, using the multi-layered structure, we were able to set the linear voltage distribution along the winding and calculate the electric field strength distribution in the potential transformer. If you search for the potential transformer on our website, you will find the example page. Here you can read about problem setup, browse the solution section, Take a look at the result pictures and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.